Alright, so we're doing relativistic mechanics here. It's a pretty simple thing. This basically boils down to Einstein's equation, E equals mc squared, this very famous one. I'm sure you have heard of it, most people have, but in reality this is not really the full equation. The total energy of something is actually E equals gamma times what we'll call the rest mass times c squared. And this is the actual real more version for the total energy of something. But if you notice, it has this gamma term, and this gamma term involves motion. Remember, gamma is 1 over the square root of 1 minus v squared over c squared. So if this is the actual equation, how do we always end up talking about this one? Well, because this is for objects that are stationary. This is what this would reduce to, because if v is 0, then this just becomes 0, and this becomes 1 over 1, and gamma just becomes 1 at v equals 0. So this just becomes E equals m naught c squared. So at rest, that's why we want to put this little m naught. We're going to call that our m naught, our rest mass, because that's essentially the mass of it that you measure while it's not in relative motion to you. So if I take it and I put it on a scale, while I am stationary with it, relative to it, we're both stationary. It's almost like a proper mass. Then it becomes m naught, and then we could do the same thing here. This is m naught. It's the rest mass. So how much its mass appears to be when you're at rest with it, when you're in the same frame with it. So we have this E total here. We could take this idea and say that, well, this is E total. This is going to then include both energy while it's moving and energy while it's sitting still, because if it's sitting still, its energy doesn't go to 0, right? So if we think about this, that means that this total energy has a part that is kinetic due to motion and a part that would still be remaining if it came to rest. So we could then say that kinetic energy, all right, relativistic kinetic energy, is equal to this total energy, which includes the energy while it's at rest and whatever energy is added on by this gamma factor while it's moving, minus its energy while it's sitting still. So it's rest energy, m naught c squared. And this gives us a nice little equation for kinetic energy. And we can take it one step further. Go ahead and go E kinetic is equal to gamma m naught c squared minus m naught c squared. Okay, and this is our second little result. This is kinetic energy right here. Okay, and think about that little derivation there. It's kind of a hand-wavy one where you have to accept that this is the equation to begin with. But if you accept this, then this works, and this should make sense. If you want a more in-depth derivation, you can look up and find other ones that aren't really necessary. You don't have to know them, so I'm not really going to go through it, but you can integrate over work, and you can go through this integral, putting in relativistic terms and doing some substitution methods, and ultimately you can derive out with gamma appearing and all that kind of stuff. This will derive out and ultimately give you this here, because remember, this is work, this is energy, and so you can do this integral and get it. Not a bad thing. Look it up, see it once, try and follow through it, but it honestly takes up more space to go through it in detail here without just skipping a bunch of steps than I really want to, and it's a waste of time. So just take a look, and you don't really have to know it. That's just if you want to. All right. So this equation is pretty important. This is your kinetic energy. This is your total energy, and those can both be very useful. Now, if you look at this kinetic energy, we've got this gamma factor in here. Remember this gamma factor? It basically causes things to asymptote at a speed of c. And so if we draw out a graph of kinetic energy versus speed, so this would be speed down here, and this would be, kinetic energy here. Well, classically speaking, we would just get something that went up, because remember, classically speaking, and this is a good point to bring this up, is classically speaking, kinetic energy, right, equaled what? 1/2 mv squared. And if you take this relation here and you go through and you do some series expansions on it, like a Taylor series, if you've done those yet, you go through and you can expand this out and take a couple terms off it, and you actually get this whole thing will reduce down to this for a small v. If v, for v much, much smaller than the speed of light, which is what we live in every day, so this one would appear to be correct. But anyway, if we look at this old classical, purely classical equation, you have that v squared, and you're going to get that parabolic shape, right? And it's going to go up like that. But if we look at this relativistic version, you can see this with this gamma here, we're going to hit a blockage here when we get up near v equals to c. And so at the speed of light, we'll have this asymptote. So if we go straight up with this, now at first these two at low speeds, they're going to be very similar. But as you get higher, they start to diverge. And then, of course, this one will asymptote up and never actually get to this speed of c. It won't allow you to have that, so your kinetic energies are held below that line. And so this is relativistic, and would be the classical version here, and you get something like that. And there's a difference there between how they go. At these low speeds, they're very close, pretty much indistinguishable, but as you get up closer to the speed of light, they diverge by a large margin. Okay, so that's relativistic energy. Good to apply this to different problems and everything like that, and you can do some practice ones on that. The next thing we're going to talk about is relativistic momentum. Okay, and this derivation is very long, and so there's no way I'm going to show here. If I remember correctly, it takes quite a lot to derive this, but you ultimately get just a very familiar kind of result. It's basically just relativistic momentum equals gamma times the rest momentum, or rest mass times v. And you get this result here. There's not a lot more to say about it than that, but this is basically the result for relativistic momentum. Now, the interesting part, of course, you can use this, you can make use of this, but the interesting part is when you combine this with the idea of energy. So momentum and energy, relativistically. All right, this one. So the way this can be done, and this is, I'll go ahead and show you this derivation because it's kind of neat, but it's p squared c squared. All right, so if we do that, p squared c squared, that's this, right? What are we going to get? We're going to get gamma squared, m naught squared, and then c squared times v squared. Right? We have this c squared. Oops, I probably should have reversed the order on this. Hold on a second. I'm getting ahead of myself, I think. So it would have been p squared, m naught squared, v squared, c squared. Okay? And so you get this. And then we can do a little bit of a few little algebra tricks here. Gamma squared, m naught squared, and we're going to do v squared over c squared, and you'll see why we do this in just a little bit, and then this becomes c to the fourth. All right, and then we go to the next line, and we're going to add and subtract something from this. So this is gamma m naught squared, gamma squared, v squared over c squared, c to the fourth, and then we're going to subtract gamma squared m naught squared c to the fourth, and we're going to add it. Gamma squared m naught squared c to the fourth. We're going to do both of those. And then we're going to take these first two terms here, and we're going to combine them, and we're going to factor out, and you're going to get gamma squared m naught squared c to the fourth times v squared over c squared minus 1, and then plus that last term, gamma squared m naught squared c to the fourth. And so if we look at this last term, which I just carried down, but this last term, what is that term? Well, if you remember from before, what is energy? E equals gamma m naught c squared. And that then makes that term equal to E squared, right? So it's just E squared, right? E, well, total energy. I should have labeled that total energy. It's E total squared. And then look at this part over here. This is where we have to do another little bit of work over here, but we want to get this into a more useful form. Basically, I want to go ahead and just expand this gamma. Well, this is gamma squared, right? Well, gamma squared, what is it? Gamma squared is 1 over, and remember for gamma it was the square root of 1 minus v squared over c squared. Well, now we're squaring it, so it's just 1 minus v squared over c squared. And if you look at this, I have 1 minus v squared over c squared. That's this gamma squared. And I have v squared over c squared minus 1, which means these two things are the same except for a factor of -1. In other words, what I mean is I have negative m naught squared c to the fourth. And so I'm going to take a negative out of this, which allows me to switch the sign on both of these. I'm just multiplying by -1 and at the same time dividing by it. You should know that kind of trick. So this is 1 minus v squared over c squared now. That's what happened in the parentheses. And then gamma squared, as we just found, is gamma squared is 1 over this. So that puts in the denominator a 1 minus v squared over c squared. All right? And then these two terms will just cancel. Okay? And so that leaves me with minus m naught squared c to the fourth plus energy total squared equals p squared c squared. And if we rearrange that a little bit, we have a new equation for total energy, and that is p squared c squared plus m naught squared c to the fourth. And this is a very useful relation right there, okay? And so it allows us to have a nice relationship between energy and momentum right here. And so it's very useful for particles and things like that. And another little thing is, well, you can even apply this to things that don't have a rest mass. And what doesn't have a rest mass? Things like a photon. For a photon, m naught equals 0. And so for a photon, right, where m naught equals 0, what does this equation become? It becomes E squared equals P squared C squared, which is just E equals PC. And now we have an equation that relates the energy in a photon to its momentum, right? And we already know how to find the energy in a photon anyway. And so now we have a way to actually relate that to the momentum of a photon. And this tells us essentially that light carries momentum. And it carries inertia. So these, and since light's an electromagnetic field, it's telling you that light or that electromagnetic fields carry momentum, which they do. Otherwise, NASA would be wasting a lot of money trying to make those big solar sails. I'm sure you've seen those like in Star Wars and stuff and everything, but they try to make these big reflective solar sails that catch light coming from the sun and actually like drag you through then or push you through the solar system, kind of like a sail on the wind would do. So that is very important. And then if we look at this, this actually helps us get another invariant quantity that becomes very useful. Well, remember, look at this little part right here, this rest energy, right? Well, rest energy, right, we talked about it above. This rest energy, let's call it E naught, is m naught c squared, right? Well, this is made up of two invariant terms. The speed of light is invariant. It doesn't change no matter who's looking at it. And rest mass doesn't change no matter who's looking at it because it's defined as the mass of it when you're at rest with it. So these are two invariant quantities. Well, multiplying two invariant things that don't change gives you another invariant thing. So this means that E naught, therefore E naught is invariant. And also then, of course, so is E naught squared, which would be this right here. So E naught squared is 2. And so if we rearrange this equation, we can call it E naught squared equals, we're actually going back this way, but E total squared minus P squared C squared. That means that if this is invariant, then this term is invariant. That the difference between the energy and this momentum term, this is an invariant quantity, right? So that term, right, this term here is invariant. And it's another one of these things that no matter what reference frame you're looking in, right, that this term is invariant, okay? So that guy, he's pretty important. Now, the reason he becomes super important is actually, or at least the way I know it the most is, if you look up Einstein's field equations, there is, the left side of the equation is all about how space is curved and how all that works, whereas the right side is all about what matter is there. And the tensor that's on the right-hand side of it is called the energy momentum tensor. At least that's one of the names of it. And it's a invariant tensor because tensors are designed to be invariant because that's the only thing that we can really measure consistently is these invariant things. That's why the whole general relativity is all about tensor mechanics. And so this E squared, P squared, P squared, C squared is actually what's there. Because if you think about it, if I look at somebody flying across the sky and I'd say, oh, they have kinetic energy, and I would calculate it according to how fast I saw them going, right? That would be from our kinetic energy equation, right? So I'd say, oh, look, they have kinetic energy, and it's based on how fast I see them going, that gamma. And the same thing with momentum. But someone moving at a different relative velocity would measure a different gamma factor for each of them, and then there'd be a disagreement about how much kinetic energy an object has. Because think of if you're moving in the reference frame with the object, then you would say that there was no kinetic energy because this would become 1 and it'd be m naught c squared minus m naught c squared. And so you'd say there's no kinetic energy because it's at rest relative to you. And same thing with momentum. You can change the momentum depending upon which reference frame you are looking at. So the fact that this quantity then is invariant is very useful because then what you can do is you can measure both your kinetic energy according of an object in your reference frame and its momentum, and you can combine them into something that is then an invariant quantity. And that's what's done a lot in general relativity and some here too, because this becomes the invariant thing. It's the actually that tensor has a bunch of energy densities and energy flows and momentum densities and momentum flows, whereas this is just that. But it's ultimately what's leading to the relationship of energy and momentum being what everybody can agree on, or at least the difference in them. And so this is, if you look at this, very similar to our previous invariant quantity, the space-time interval, even having this negative sign in here where it's very close, but it's kind of a hyperbolic thing, again, going with that hyperbolic type space where we have a minus instead of a plus, but very similar to the Pythagorean theorem. All right, I think that's pretty much it. Oh, no, there's one more thing. I wanted to mention that sometimes you'll hear people talk about acceleration, relativistic acceleration. Well, special relativity does not really deal with accelerating frames because that Minkowski space that we talked about before is supposed to be a flat space. And if there's accelerations, then you basically have a non-flat space, and it starts to get into the realm of general relativity. So anytime you see someone talking about special relativity and accelerations, they have to be talking about very small accelerations where it's still close enough to a flat spacetime that we can use that Minkowski space and we can use special relativity to describe it type thing. That's that flat spacetime still then is a good enough approximation. But if you get into a lot of accelerations, then you have to move into the general relativity realm of things. All right, I think that is actually it this time.